Okay, thank you very much, Birger, for that introduction. And let me say first, what a pleasure it has been to visit your beautiful and wonderfully efficient city here and learning about some more about the very impressive work that's being done here at NUS. So what I'd like to do for you today is tell you a little bit about some of the work that we have been doing in my labs at UT Austin on applications of semiconductors in quantum and energy. And what I mean here by semiconductor physics and devices across length scales is the following. If we think about semiconductors and different applications of these materials, there's really a tremendous range of sizes of the characteristic structures that have to be made. So for example, for semiconductors in quantum applications, typically we're looking at making structures that are kind of in the nanometer to micron scale of sizes. And as an example of this, I'll tell you about some of the work that we've been doing in my lab using various types of scan probe techniques to measure the strain tensor in atomically thin materials, transition metal dichalcogenide semiconductors with nanoscale resolution, tens of nanometers, and then how some of these ideas related to highly inhomogeneous strain distributions in these materials relate to single photon emission that can be observed in transition metal dichalcogenides. And then I'll move on and go to sort of the opposite end of the size scale, where for many applications in sustainable energy, all right, it's necessary to be able to make structures that have sizes ranging from centimeters up to potentially meters and ultimately larger. And as an example of this, I'll talk about some of the work that we've been doing, taking various ideas from the semiconductor device physics and manufacturing field and applying them to the problem of designing and fabricating photoelectrodes for green hydrogen production. That is, splitting water molecules into hydrogen and oxygen using solar energy. All right, and if time permits, then I'll talk a little bit about some of the things that we've been doing very recently that sort of establish a connection between these very different regimes, where we have been thinking about how nanoscale strain distributions that you can get in certain types of these structures that we've been looking at for photoelectrodes can actually very strongly influence carrier transport in a way that improves the performance of those types of photoelectrodes. The other point that I want to make, which I think you'll see throughout the talk, is that even though there's this tremendous range of the sizes of structures that one wants to make, it's essentially always the case that it is necessary to be able to control the structure and understand the properties of all these materials at the nanometer scale, even when you're making things that are centimeters to tens of centimeters or larger. Okay, so what I'll do first is tell you about some of the work that we've been doing on atomically thin transition metal dichalcogenide semiconductor materials. So I know there's a tremendous amount of work here that's being done on two-dimensional materials generally. What we're looking at here is a subset of these materials, specifically transition metal dichalcogenide semiconductors. All right, so these are materials that have a layered structure, and within each atomic layer, one has transition metal atoms. So in our case, either molybdenum or tungsten, covalently bonded to chalcogens, sulfur or selenium. All right, they form individual layers that are 3 atoms thick, and then these layers are stacked on top of each other to create the bulk material. Okay, and the different layers, they interact only through van der Waals interactions. Okay, so then it's possible to separate the layers from each other and reduce them down to just a single layer that is 3 atoms thick. All right, and as you get to this atomically thin limit, or maybe a few of these layers together, then there are a number of very interesting properties that arise. One is that in this limit, the materials are extremely flexible mechanically. All right, so you can have high levels of strain and very inhomogeneous spatially strain distributions. as one makes the transition from multi-layer material to monolayer material, there's also a transition in the electronic structure from having an indirect band gap for multi-layers to a direct band gap for monolayers. And that has major implications for the application of these materials in optoelectronic devices. There are also topological aspects to the electronic structure that arise. Okay, so there are a number of applications that people are interested in exploring of these types of materials. And the one that I will focus on here is the use of transition metal dichalcogenides for single photon emission, right? So essentially being able to emit one photon at a time rather than many at a time. And this is one of the fundamental building blocks for certain approaches to quantum communications and quantum information science. And essentially what's done here is the following. This has been observed in a number of different monolayer transition metal dichalcogenide materials. And the most common one for this application is tungsten diselenide. So that's the one that I'll focus on here today. And this behavior of single photon emission arises when one has these materials with highly localized regions of tensile strain. So just stretching the lattice a little bit. And so there are a variety of ways to create these types of structures. One shown here is basically that you take a monolayer of these materials and you just sort of drape it over an array of nanopillars, and then you have tensile strain near the apex of the pillar. You can also do similar things by transferring these materials onto an array of nanoparticles, or by using an AFM tip to sort of push the material into a soft substrate as shown here. And what happens to enable single photon emission is believed to be what's shown here. When you have tensile strain, then the band edge energies shift in a way that reduces the energy band gap, okay, so that excitons in these materials, bound electron hole pairs, move towards the region with the greatest tensile strain. And then at the same time, because these band edge energies are coming down, then there is a hybridization between the dark exciton band. That's the exciton band where optical recombination corresponds to a spin-forbidden transition. There's a hybridization between the dark exciton band and a defect level in the material, such that when the exciton recombines, a single photon can be emitted from the defect level. Right, so that's the basic idea. And the specific questions that we wanted to try to address in what I'll describe to you today were, first, given the role of strain and the importance of strain in realizing this behavior, are there ways that we can characterize the nanoscale strain distribution of these materials in geometries that are similar to the ones that are typically used for single photon emission? And then the second question that we'll try to address here is there a way that instead of creating essentially static strain distributions as shown here, is there a way that we can dynamically and single photon emission behavior? So I'll talk first about how we have looked at measuring nanoscale strain distributions. And we do this by using a scan probe technique known as Kelvin probe force microscopy. Okay, and the basic idea is shown in this slide here. So this is an AFM-based technique, and the sample structures that we create consist of essentially a hot metal contact here into which we have etched these cavities in an underlying SiO2 layer. And then we have these submicron scale mesas over here. And then we transfer monolayers of TMD materials, specifically MOS2 in this case, onto that surface. And so this mesa here gives us a geometry that is similar to what is used for single photon emission. All right. And then in addition, we have a backgate electrical contact to the underlying silicon substrate. And what that allows us to do is we apply the backgate voltage, then it's possible to modulate the band edge energies and the carrier concentrations in the TMD layer. All right, and we'll see why that's a useful thing to do in a minute. This over here shows just an optical microscope image of an array of these holes. I know it's a little hard to see in here, array of these holes. This region outlined in red is where there is a monolayer of molybdenum disulfide, and this is an AF image of one of the holes shown over here. All right. Now, what happens in the Kelvin probe microscopy measurement is that you have a probe tip and a sample, and they have different work functions. Okay, so when you bring them into close proximity, there's a potential difference between them. And what happens then is that a bias voltage is applied to the tip to zero out that potential difference. And that gives you a way to measure local variations in the surface potential, the work function of this material. Okay, so that's the standard Kelvin probe microscopy technique. What we have here in addition is this backgate contact. And what happens there is that if we apply, say, a positive bias voltage here, then that moves the energy levels down. And then there's a corresponding lowering of the energy levels in the sample, in this case, monolayer MOS2. But that decrease in the energies is affected by the fact that you can have carrier accumulation in the MOS2 layer. So it doesn't exactly track the backgate voltage that is applied. And so if we look at this in more detail, the main point here is that what happens is that when we apply a backgate voltage, say a positive backgate voltage in this case, then these energy levels move down. And as the conduction band energy, edge energy approaches the Fermi level, then there is accumulation of electrons in this layer. So there's a capacitance associated with that electron accumulation. This is referred to as the quantum capacitance. And that combines with the capacitance of the oxide layer over here to give us the relationship between the backgate voltage that we apply and the change in the potential in the sample layer. All right. And if we construct a simple capacitive model for what should happen here, then what happens is that at small gate bias voltages, where the conduction band edge is fairly far away from the Fermi level, there's not very much modulation of the charge in the MOS2 layer. And so the surface potential roughly tracks the gate voltage. But then for higher gate voltage, as the conduction band edge approaches the Fermi level, there's much more modulation of that charge. And what ends up happening is that because of the high density of states in the MOS2 layer, once conduction band edge gets very close to the Fermi level, then they don't shift anymore. The Fermi level is pinned at the conduction band edge, and the surface potential no longer depends on the gate voltage. So that's what happens in this measurement. And if we actually do that measurement and look at the dependence of the measured surface potential through the tip voltage on the gate voltage, then in fact it shows exactly this kind of behavior, right? And we can show that that is specifically associated with carrier accumulation in the TMD layer, because if we do the measurement without the TMD layer present, then the surface potential exactly tracks the gate voltage. But then once the TMD layer is present, then we get the behavior that I described and showed over here. All right. Now, one of the implications of this then is that if we look at a situation where there is some modulation locally in the energy of the conduction band edge in this material, so this is now looking laterally in the material, and this is the situation that we have when we have localized strain, because the strain induces a lowering of the conduction band edge energy. Then as we apply this backgate voltage, going from 0 volts in this schematic up here to some large positive gate voltage, then the conduction band edge energy is gradually drawn downwards and then eventually gets pinned at the Fermi level. And this happens in such a way that in this strongly pinned situation down here with the large positive gate bias voltage, the local vacuum level is a reflection of the variation in the surface, in the conduction band edge energy that existed in the absence of the gate bias voltage. And that's shown over here, right? So this is the Kelvin probe measurement of the surface potential at a large positive gate bias voltage. And what you see here is that, in fact, we do see this region corresponding to this mesa over here where there is localized tensile strain, and there is this lowering of the, essentially a map of the lowering of the conduction band edge energy due to that strain, all right? Now, what we can then do is take that variation in the band edge energy and translate that to strain, because it's known how the band edge energy depends on the strain for these materials, right? So these are the deformation potentials that have been calculated for all these materials. They turn out to be dominated by the hydrostatic component of strain, which is the change in the volume of the unit cell, okay? And so since it's known what the energy of the band edge is as a function of the strain, then we can pretty directly go from this map of the band edge energy to a corresponding map of the hydrostatic strain, all right? And we can get this with spatial resolution on the order of tens of nanometers, okay? Now, you might ask, okay, that was a pretty long path, right, that we're following to get this. So is there some way that we can corroborate the strain distribution and see, okay, does it really look like this? So there is another way that we can do this, which is that it's also possible to extract information about the strain from just the surface topography, which can be measured in conventional atomic force microscopy. Okay, so this is done basically by using tools from mechanical analysis of the deflection of thin plates. So the TMD layer is acting as the thin plate in this approach. And using the Foppel and Karman equations from this field, one can solve this equation over here, right? H here is measured in AFM, okay? And so this is essentially something that's known. You can solve this equation here for chi, which is what's called the area stress function. Once you have that, then if you look at the second derivatives of that, that gives you the stress tensor, which then you can combine with the elastic stiffness constants to get the strain. All right, so that's the basic idea. And if you use this approach, just from the AFM topography, you get this distribution here for the hydrostatic strain. All right, up to values in this case of roughly 0.5% strain. This is the shear strain that you get using this approach. And if you compare that to what we measured using the Kelvin probe approach, then what you see is that the magnitude of the strain that you see is very similar, all right? Not only the central feature over here, but some of the peripheral features here and here, all right? But you see that there's much more fine scale structure to this than you get from the AFM-based approach, all right? So then you might ask, okay, well, is there real physical information in this fine scale structure, or is it essentially an elaborate way of measuring noise? So to determine the answer to that, one of the things that we can do is try to understand what some of the observable implications might be of having these kinds of variations in strain. And it turns out that one of the very interesting behaviors that we can get from this is what's known as piezoelectricity. Okay, so to analyze piezoelectricity in these materials, what we first need to do is to go from just the hydrostatic strain to the full strain tensor. And we can again get that from this thin plate deflection analysis. It turns out that the hydrostatic strain can be used in this expression here to again get the area stress function. And then from that, you're able to get the stress and then the strain tensors. Once we have full strain tensor, then we can see what that predicts about the presence and the nature of piezoelectricity in these materials. So piezoelectricity, which as many of you probably know, is essentially a coupling between stress or strain and dielectric polarization in a material. It's actually a very interesting behavior in these transition metal dichalcogenides, because if you have bulk material, right, where you have these layers stacked on top of each other, then successive layers are stacked on top of each other with opposing orientations. So that structure is centrosymmetric. And in order to have non-zero piezoelectricity, the material has to be non-centrosymmetric because it's governed by a third order tensor as shown here. Okay, so bulk TMD materials are not piezoelectric. However, if you have a monolayer, then you only have this, right? The structure then no longer has inversion symmetry, and the piezoelectric coefficients that you can get are non-zero and actually can be quite large, okay? And one of the things that is then very interesting is that if you have spatial variations in the piezoelectrically induced dielectric polarization, then you get corresponding bound charge, electrostatic bound charge densities in the material. All right, and more specifically, that bound charge density is given by the negative of the divergence of dielectric polarization. Okay, and if you take the dielectric or the piezoelectric moduli of these materials, and you just calculate in the back of the envelope way, what kind of charge density would you get through this mechanism if you had, say, 1% strain variation over 100 nanometers, right, which is very consistent with what we had measured, then in bulk form, you would get something of the order of 10 to the 17 electronic charges per cubic centimeter. In a monolayer, that corresponds to something of the order of 10 to the 10th electronic charges per square centimeter, which is actually quite a lot, right? So it turns out there's a precedent for piezoelectric effects being very important in understanding the behavior of certain classes of semiconductors. And this precedent actually comes from group 3 nitride semiconductors, which technologically now are of enormous importance. It's the basis for all solid state lighting that we have now, among other things. And in some work that my lab did back in the 1990s when we were at UC San Diego, we showed that piezoelectrically induced polarization in group 3 nitride heterostructures played an extremely important role in allowing two-dimensional electron gas structures to be realized with very high electron densities, because you would form a sheet of positive bound charge at this interface through actually a combination of piezoelectricity and spontaneous polarization. And that electrostatically attracted very high densities of electrons that enable things like high power transistors and so forth to be realized. And this is now really a central part of how people in the field have to think about group 3 nitride heterostructures. So there's certainly a precedent for these effects being important. If we come back then to the TMDs, all right, the path that we're following is that we've used this Kelvin probe microscopy technique to determine the hydrostatic strain distribution. From that, we can get the full strain tensor. We combine that with second harmonic generation to get the orientation of the crystal relative to these axes. And then we can calculate the dielectric polarization and the corresponding bound charge. We get this over here, right? And you can see that these bound charges have magnitudes up to a few times 10 to the 10th, right, which is about what we would expect. We can then take those bound charge distributions and then solve Poisson's equation for the corresponding electrostatic potential. We get this. And then if we go back and we look at the Kelvin probe microscopy measurements, but now at negative gate bias voltage, where carriers are depleted, okay, so that you actually unscreen the piezoelectrically induced bound charges so that they can be observed, we get this type of surface potential map over here. If you sort of squint at it, you can see that maybe this looks like a fuzzy version of this distribution over here. And if you look more carefully at, say, this feature here, where there are these two features and then a gap in between in the surface potential, and you look at the corresponding region in the electrostatic potential calculated from the strain over here, that's shown in this line plot. You can see that they actually agree quite well in terms of both the magnitude of the modulation and the spatial extent. So this really quite strongly suggests that what we see over here really are variations in strain and corresponding properties, in this case, piezoelectricity, at tens of nanometers length scales. Okay, and then this opens up the door to being able to characterize strain distributions with very high resolution in a variety of different types of TMD-based structures. Now, I'll come back now to this question of single photon emission, all right, where what we wanted to do was to see if there was some way of, instead of just having static strain distributions as shown over here, we can dynamically modulate the strain. And one of the approaches that we have looked at to do this is what's shown over here. All right, so what we do is we have a monolayer of, in this case, tungsten diselenide, right? It is suspended over a micron scale cavity, all right? And then there's a backgate contact over here. And what happens then is that when we apply a voltage, right, between the tungsten diselenide and the silicon backgate, there's a capacitive electrostatic interaction between the monolayer and the backgate. It leads to electrostatic attraction so that this monolayer is deflected downwards and you get tensile strain from this behavior, all right? So this just shows a three-dimensional view of the same thing. And if we do some simple modeling of this, all right, where we equate the energy associated with strain in this material for a given deflection with the electrostatic energy of this capacitive interaction, then what this would predict is that for the typical dimensions of the structures that we're making here, then we can get to strain on the order of maybe a few tenths to 0.5%, which is sufficient for observing single photon emission at backgate bias voltages on the order of 20 to 40 volts, which is very achievable. All right. Okay. So what I've shown here is just an image of an array of these cavities that we've created. Right. So you can see, right, they're about 150 to 200 nanometers. In this case, a little over 150. All right. This is an optical microscope image of a tungsten diselenide layer transferred onto this array, and the region corresponding to monolayer material is highlighted here in pink. This shows an AFM image of a region of the holes that are covered by the tungsten diselenide, and then some holes over here that are uncovered. And by looking at line profiles of each of these, we can see that indeed the tungsten diselenide monolayer bended over the hole, and there's a little bit of sagging that occurs because of the way the layers are transferred. Now, what we also want to see is whether this electrostatic approach actually can lead to downward deflection and therefore strain in the tungsten diselenide monolayers. And if we, so here I've shown AFM images with bias voltages of 0, 5, 10, and 15 volts. All right. And what we see is that indeed there's this downward deflection of the monolayers, and the amount of the downward deflection is actually quite consistent with what's predicted by this simple model, right, that I described. So, so that gives us a way to design structures and predict how much strain should be possible to produce. Okay, we can then take these structures and do photoluminescence measurements in a cryostat. So what I've shown here are photoluminescence measurements at 100K, okay? And so we see the dark exciton peaks over here and over here for the different polarities of bias voltages. These peaks clearly shift in a way that corresponds to the presence of tensile strain. And by looking at the magnitudes of these shifts, then we can see that in this case, we're getting to levels of tensile strain that are roughly 0.2% or maybe a little bit higher in this case. All right. We can then go from here and look at photoluminescence at 4K. And what we see in this case is that we have the well-known emergence of these very sharp luminescence peaks that are typically associated with light emission from localized emitters, right, associated with defect levels. And these then are often associated with single photon emission, okay? There's sort of this interesting dependence of the behavior of these localized emitter peaks on the bias voltage that's applied. All right, we see that when we apply this bias voltage in either polarity, there's a large reduction in the broad background photoluminescence. There is an increase in the intensity of these localized emitter peaks relative to the background, and there's a reduction in the line width. All right, all of which are favorable for single photon emission. If we look then more specifically at what are generally considered to be the signatures of single photon emission in these materials, what we see is the following. So these are measurements from this region of one of the samples over here, and specifically from this particular location. So if we look at one of these localized emitter peaks, you can see that it has a very narrow line width, a little under 1 MeV in this case, all right, which is in the range that is generally required. We see that as we increase the excitation power for the photoluminescence measurement, there's a saturation in the luminescence intensity, which is also a signature of single photon emission. And then we see that the lifetime that we observe is in the range of 2 or 3 nanoseconds, which is also about what you would want to see. The definitive evidence of single photon emission is generally considered to be this 2-photon correlation measurement. All right, so this is essentially a measurement of what is the probability of having photons emitted with a certain time delay between them, and if that and what you would expect for single photon emission is that at a delay of 0, the probability should be vanishingly small. And the criterion that is generally applied to show that there's single photon emission occurring is that this correlation at 0 time delay should be less than a half, okay, less than 0.5. And what we see here is that in this particular case, without any bias voltage applied, it's not quite there. You get a G2 of 0.55. But once we apply a bias voltage, in this case it's minus 30 volts, we get to 0.4, which is clearly beyond that threshold. So what this series of results is showing then is that it is possible to dynamically modulate strain in these structures in a way that then also modulates the luminescence properties, and in particular here, the observation of what's generally considered to be the proof of single photon emission. And it opens the door to really doing more detailed studies of how strain influences luminescence and single photon emission, and perhaps using an approach like this to control the to modulate the behavior of single photon emission. So that's basically what I wanted to say about the TMD materials. And what I'll do next is move on to kind of this range of much larger structures, but where understanding and control of material properties of the nanoscale is still very important. And I'll describe some of the work that we've been doing using ideas from various parts of the semiconductor device physics and manufacturing communities to develop these photoelectrode structures for solar-driven water splitting. Right? I think I probably won't have time to talk about this over here. Okay. So first, I guess this is a more quantum audience, and so one might wonder, why is it that this problem of producing hydrogen is an interesting and an important one? Now, in the news, okay, if you hear about hydrogen, then mostly what you probably hear about is fuel cell vehicles. And then maybe if you're paying close attention, you might hear about splitting water molecules to form hydrogen and oxygen as a method for storing intermittent renewable energies, such as solar or wind, okay? However, even if neither of these things ever happened, right? So no one ever made another fuel cell vehicle, people didn't try to do this storage. The existing market for hydrogen is over $170 billion a year. So it's a major economic activity. And it's also something that is of global societal importance, because one of the main applications of hydrogen is to combine it with nitrogen to make ammonia, right? That's the Haber-Bosch process. And ammonia is a key constituent in artificial fertilizer, right? So if we didn't have this, then it would have major global societal implications. So this is a big market. It's growing at several percent per year, even without any of this, okay? Now, one of the challenges here is that the typical ways that are used to produce hydrogen commercially are not environmentally friendly. They're almost all commercial hydrogen production is based on fossil fuels, okay? And one of the most common approaches, probably the most common approach, is what's called steam methane reforming. Right? So you take methane, CH4, you combine it with water, H2O, you heat them up together, and through a series of reactions, you end up getting hydrogen and carbon dioxide. Okay. And for each, say, kilogram of hydrogen that you make in this way, you make several kilograms of CO2, and in many cases, that just gets released into the atmosphere. So this turns out to be responsible for close to 1 billion tons of CO2 emissions per year. Right, so really a lot. So it would be very nice if there were a way to make hydrogen without having all these CO2 emissions. That can be done by splitting water molecules to form hydrogen and oxygen. All right, the more mature technology for doing this is what is known as electrolysis. Okay, and so the idea is that you have a cathode and an anode, you put them in an aqueous solution, you apply a voltage, and that splits. If the voltage is sufficiently high, the water molecules are split into hydrogen and oxygen. If the electricity that is used to drive this comes from renewable sources, then you can minimize production of CO2. All right, another approach is to do what is known as photoelectrochemical water splitting. So here, one has a photoelectrode. This is typically some semiconductor absorber with catalysts for either an anode that is producing oxygen or a cathode that is producing hydrogen, either singly or together. And the idea is that one has absorption of sunlight in the absorbent material, creates electron-hole pairs, and then those electrons and holes are used directly to perform one or both of the water splitting reactions, either the oxygen revolution reaction or the hydrogen evolution reaction. So what I'll describe to you here is looking at this approach, photoelectrochemical water splitting. So this is something that has actually been known about for a long time. Right? The first paper reporting this is this very famous paper by Fujishima and Honda, showing that this approach can be used to split water molecules into hydrogen and oxygen. And basically, the way it works is that if you have a semiconductor absorber material and you shine light on it, say sunlight, then you create electron and hole pairs. And if the band gap of the semiconductor is sufficiently large, it has to be larger than the difference in the redox potentials for the water splitting reactions. This difference is 1.23 electron volts. So you need slightly larger band gaps. And if they're properly aligned with the redox potentials, then the electrons can participate in the hydrogen evolution reaction, H plus to H2, and the holes can participate in the oxygen evolution reaction, OH minus to eventually O2 and H2. Okay, so this is known, but it's an extremely hard problem scientifically and technologically. Okay, and because there are several requirements that have to be satisfied in order to get this to work. Right, so you need absorber materials that are good absorbers of sunlight. So that means you typically want semiconductors that have moderate energy band gaps, right? Band gaps that are typical of solar cells or maybe somewhat larger. So materials like silicon, gallium arsenide, and so forth, all right, and a few others. You want the energy bands to be properly aligned with the redox potentials. You also want these absorber materials, ideally, to be resistant to decomposition, corrosion, or oxidation in the presence of these water splitting reactions. And that's actually a major issue because materials that are good solar absorbers generally are not stable solution in the presence of these reactions. Materials that are stable are usually wide bandgap metal oxides, but those are very poor solar absorbers. So there's already this conflict between what's required for efficient solar absorption and stability. And then, of course, for these types of large-scale applications, you want the materials and the fabrication processes to be very cheap, and you want them to be massively scalable. Okay. Now, if you go to someone who thinks a lot about semiconductors and you say, I want something that is very cheap and massively scalable, then the answer that you're likely to get is, well, you should use silicon. And people used to say, microelectronics demonstrates that. Now, for really massive scalability and extremely low cost, you can just look at solar cells, which are mostly made from silicon. So, silicon is nice because it is low cost on a semiconductor scale. It is massively scalable. It's a good solar absorber, but it has this problem that it's not stable in the presence of these water splitting solutions. So one approach to addressing this problem is to create what are called metal insulator semiconductor photoelectrode structures. So you have a semiconductor absorber over here, say silicon. Then you put some protective layer on its surface. All right, and typically this will be an electrical insulator. Okay, that protects it from the aqueous solution. Then you put a metal catalyst on top that accelerates the reaction, and then there you have it. So that can address the stability issue, but you've traded the problem of stability for the problem of getting the mobile carriers, the photon-generated carriers, across this electrically insulating layer, right? Now, one approach to doing this, which is mostly what has been done in the literature, is to say, well, we'll just make this protective layer extremely thin, maybe on the order of 1 to 3 nanometers. And then when it's that thin, the carriers can tunnel across them, all right? But if you really want this to be a good protective layer, 1 to 3 nanometers may not be sufficient. You really want most likely something that is several tens of nanometers in thickness. And then the tunneling probability will be essentially 0, okay? So when we first started thinking about these kinds of problems, maybe roughly a decade ago now, first thing that we thought about was, okay, well, are there materials that we can use that will serve as good protective layers, but that have favorable energy band alignments to allow for easy transport of at least one of electrons or holes, right, across this MIS structure? And it turns out that there is such a material, strontium titanate, okay, can be grown by molecular beam epitaxy in extremely high quality on silicon, okay? And in fact, strontium titanate is a material that has been explored for water splitting applications for quite a long time, but because it has a large band gap, it's not very efficient, okay? But it does have small conduction band offset with silicon. And so what that means is that if you look at the band edge energy diagram for a structure consisting of silicon, strontium titanate, and then metal catalyst, electrons can move very easily across the structure. So that was the basic idea. So we made a bunch of these structures. We were able to show that, in fact, one does have very good conduction of electrons across this layer. And also, if you make photoelectrodes, photocathodes in this case, right, which are performing the hydrogen evolution reaction, then there is very little dependence of the performance of these structures on the thickness of the strontium titanate, which is what you would expect if you have this kind of picture over here. If what was really happening was tunneling, then the current would decrease exponentially with increases in the thickness, and that's not what we observed. So we went ahead with this. We also incorporated some ideas having to do with using multi-layer catalysts to optimize both catalytic performance and the electronic structure of the photoelectrode. There were also ideas that have been demonstrated in the literature recently at that time, where by lithographically patterning these photoelectrodes and then the catalysts on these photoelectrodes, then it was possible to, if you made the sizes and spacings comparable to the minority carrier diffusion length, then you get significant increases in performance. Okay, so we followed through with that, but then we pushed this to even smaller structures. Okay, 50 nanometer pitch, 50 nanometer diameter, 100 nanometer pitch. All right, and what we saw was that when you went to this very small size scale, you actually got much better performance in the photoelectrodes. And so we were able to show that using these approaches, you could get very good performance on an absolute scale and very good stability as well. All right, I will skip what we've done to explore why that is the case, and instead sort of move on to where this might lead to. All right, so once we demonstrated this, we started thinking about, okay, are there ways to generalize this approach? All right, but that turns out to be quite hard, right? partly because the idea of creating a small band offset works in the conduction band, but it doesn't work in the valence band because for all these metal oxide materials, the valence bands are very low in energy. So you always have a large valence band offset. It's very hard to get good hole transport. In addition, deposition technique, molecular beam epitaxy, is great scientifically, but very expensive and not very scalable. Now, it turns out that at the same time that we were doing some of this work, there was another project going on in the group where we were looking at what's called resistive switching in metal insulator semiconductor structures. Okay, so this is a behavior where through the application of some appropriate combination of current and voltage, you can have changes in the vertical conductivity, electrical conductivities of these structures by orders of magnitude. All right, and this occurs through the formation of these conducting filaments through the oxide, which can be several tens of nanometers thick, basically through the assembly of oxygen vacancies. Okay, so we were looking at this for applications like non-volatile memory and neuromorphic computing. But then what we realize is that this is actually exactly the kind of structure that you want for a photoelectrode as well, because these filaments are good conductors of both electrons and holes. You can have a thick oxide layer on top of silicon, and then the metal can act as a catalyst. Okay, and this defective region is protected from the aqueous solution by the catalyst on top. So that was the basic idea there. Okay, so the student who was working on this, Li Ji, went ahead and sort of optimized the conditions for inducing this kind of filament formation and made both photocathodes for the hydrogen evolution reaction and photoanodes for the oxygen evolution reaction using this approach, right? The performance was reasonably good and the stability was very good, but it was generalizable to both electrons and holes. You could use different insulating layers and in fact, even different semiconductor absorbers, all right? Now, the challenge here was that to actually make these structures required a heroic effort on the part of the student who was working on this, because for each photoelectrode device, you have an array of these catalyst pads, and they have to be electrically broken down one by one. So for every device that Lee made, he had to do this like 1,000 times. Okay, and this is not scalable at all. It was sufficient to get a nice paper out of it. So what we then thought about was, okay, is there a way that we can take this idea of controlling the electrical conductivity through an oxide layer, but actually realize it using a much more scalable approach? And to do that, what we realized was that we could take advantage of certain thin film reactions that occur specifically between aluminum and either an underlying silicon or silicon dioxide layer. So this is something that is actually well known in semiconductor processing. If you have aluminum, say on top of silicon, it was known from the early days of making ohmic contacts, right? That if you annealed it to form the contact, the aluminum would form localized spikes that penetrated into the silicon, all right? And this was bad for devices because it would short out the underlying device structure, but it was good, for example, for applications like this, where you wanted to have ohmic contact through an SiO2 layer to a silicon layer. You take this structure, you anneal it, and you form just these localized contacts through the oxide, and you get a good enough ohmic contact, and you retain most of the silicon-silicon dioxide interface that gives you basically good passivation. So it prevents high surface recombination velocity. So this is sort of the cartoon version of that process. Then the full process to make photoelectrodes, in this case photoanodes, is that you have silicon, you oxidize it, deposit aluminum, you anneal it to form these spikes, you etch the aluminum away, and then you fill those voids using electrodeposition, which is certainly a cheap and scalable technique. We did this with nickel, okay, which is a good enough catalyst for the oxygen evolution reaction. So you get structures like this, where the light can penetrate through the exposed areas. You create electron hole pairs, and then the holes can move easily through to the catalyst to participate in the oxygen evolution reaction. So I will go through the rest of this more quickly. These are just some details on the details of how the fabrication process proceeds. We use this approach to make photoanodes, and you get quite good performance and extremely good stability. All right, this is a 7-day stability test, which is the longest that we could reasonably do in the lab, and there's no change in the performance of these devices at all. Okay, one of the challenges here was that in that early generation of devices, you actually had to apply a lot of extra voltage in order to get to appreciable current levels. That's bad for efficiency. Okay, and the reason this happens is because nickel is a mediocre catalyst for the oxygen evolution reaction. You can do much better with nickel iron alloys. So, however, you still want nickel to be in contact with the silicon because that gives you a higher Schottky barrier, and that improves the onset potential. So what you really want is to have a 2-layer catalyst structure with nickel in contact with the silicon, and then nickel iron acting as the catalyst on top. Okay, and if we do that, we can see that indeed nickel iron compared to, or nickel in contact with the silicon compared to nickel iron gives us better turn-on characteristics, and the optimum ratio of nickel to iron is roughly 4:1. We get large increases in the efficiency and still very good stability. And what's really interesting about this is that all of the unit processes that are required to make these structures are really quite simple, low cost, and easily scalable. They're similar in complexity, maybe even a little less complex than what is typically used to make silicon solar cells, which we know are very low cost and massively scalable. So we were able to go from, quite easily from making devices that are kind of this size, right, which is what is typically reported in literature, to doing this on full wafers. In this case, this was a 4-inch wafer, all right? And even without optimizing this at all, really, we were able to make, at least okay wafer scale photoelectrodes. This is the current voltage characteristic, basically, the LSV characteristic of a full wafer photoanode compared to a small area photoanode. It's definitely not as good because this is less uniform than the small area, but that's certainly something that can be improved with probably moderate effort. You have very similar characteristics under both a large area simulator and in direct sunlight. The current is a little bit lower in direct sunlight because of shadowing effects in the apparatus. And then to try to get a solar to hydrogen efficiency out of this, what we did was we took one of these wafer scale photoanodes and we combined it with just off the shelf silicon solar cells, all right, so that we could get sort of the full reaction occurring and extract a solar to hydrogen efficiency. We get around 6.9%. Okay, and to give you some calibration for that number, one of the standard benchmarks for the US Department of Energy for solar to hydrogen efficiency that would be required to have cost-effective green hydrogen production using this kind of approach, it's about 10%. If the performance of the wafer scale photoanode were as good as the small area photoanodes that we made, which is certainly something that can be achieved with probably just moderate effort, that's something we're working on now, this efficiency would be roughly 12 to 13%, right, which is really good. Okay, so this is something that we think is very intriguing because it really has, I think, the possibility to bend the cost curve for production of photoelectrodes for green hydrogen production to something that maybe is more comparable for the photoelectrodes to what's required for silicon solar cells, and really move in a material way towards cost-effective green hydrogen production. So, okay, so that's basically everything. And so what I tried to do in this presentation is to tell you about different applications of semiconductor structures where the size scale that is required of the structures one is making can vary tremendously, right? From sort of quantum type applications down here to energy type applications with much larger sizes, but where at every size scale, it's really necessary to control and characterize and understand the properties of these materials and these structures at the nanoscale. Okay. And finally, and most importantly, right, I'm the one up here telling you about this work, but these are actually the people who did the work. And in particular, Alex De Palma was the person who did the strain mapping work. Francis Wu was the lead on the single photon emission work. And then Li Ji, Sunil Lee, and Andy Wu were the leads on the various parts of the photoelectrode work. We've been very fortunate to have a number of great collaborators, both within and outside UT. And then these are the organizations that, the programs that paid the bills. So that's everything I have.